loop expansion of Green's function given the definition of this amputated amplitude, we can write Gn P1 to Pn as the capital P factor for the external lines times a tilde of n, that is the amplitude, that is the amputated amplitude. But then I can count, those are topological diagrams, but then I can count them in terms of the number of loops. So L equal to 0 to infinity, a tilde of n sub L P1 to Pn, and this is basically the L loop contribution. Now, if you recover H bar, on this expression, then since the propagator will be multiplied by a factor of H bar, okay, so I have wrongly positioned it. So this factor of capital P, which has n propagators, should have H bar to the power n. So this will be H bar to the power n capital P, P1 to Pn, and L equal to 0 to infinity. Since it's an L loop contribution, it has I internal lines and V vertices. So for each internal line, I will have a factor of H bar, so H bar to the power I, and for each vertex, I'll have a factor of 1 over H bar, so that is minus V. That is how an L loop diagram will be scaled. The amputated part will be scaled. And this is nothing but L minus 1 because of the identity here. I minus V is L minus 1. Therefore, so this is L minus 1, this is L minus 1. So I can take the H bar to the power minus 1 and multiply with this. This is H bar to the power n minus 1, and take that factor of H bar to the other side. So H bar to the power minus n plus 1 G tilde n P1 to Pn is given by sum over L equal to 0 to infinity H bar to the power L A tilde n L P1 to Pn. So this factor, so that means you take a n-point Green's function and you multiply with a factor of H bar. If you scale it with the right factors of H bar, this H bar factor mostly basically H bar to the power minus n is coming from the external lines. Then that will be, given by a loop expansion, and that okay. So this will have a factor capital P is missing here. So if you ignore the external lines, then the amputated amputated contribution or diagram will have an h bar expansion, and amputated piece will have an h bar expansion where the factor of power of h bar counts the number of loops. That is the result. So if you take h bar going to zero limit, then one should take h bar going to zero limit of this quantity, not this quantity. If you take h bar going to zero limit on this quantity, then you end up getting zero loop diagrams, which are only tree diagrams. So these are tree diagrams. Now, I will make a passing comment here, but will not go into the details, not at least in that in this main lectures. Is that if you take the classical theory of the scalar field with these interactions, say phi-cube or phi-4 or any higher order interactions, then of course there is a classical equation of motion for this interacting theory, which is non-linear. If you take up to phi square in the action has phi square term and then phi-cube, phi-4, etc. So the phi square term is the free part, is a Klein-Gordon action. Corresponding to that, the equation of motion is linear in the field. For the interaction terms will contribute quadratic, cubic, and higher powers of field in the equation of motion, and those are non-linear terms, and only the free part, the linear part, which is the Klein-Gordon part, can be solved exactly. The non-linear parts cannot be solved exactly, but there is a Green's function method of solving perturbatively, finding solution perturbatively of that classical equation, and that perturbative classical solution has a diagrammatic representation, which is exactly this tree diagram, where you have these tree diagrams appearing, which is the origin of that terminology, that it's a classical contribution. So this is a comment. It's a theorem actually. Classical equation of motion of interacting theory can be solved using Green's function method perturbatively. Various terms in this solution can be represented diagrammatically, where only tree level Feynman diagrams appear. So let's look at some examples. If you calculate g1 of x, then you have these diagrams. So this is one loop and has a contribution at order h bar. These three diagrams appear in two loops, and they have contribution at h bar square. And on the left hand side we have g1, because for n equal to 1 this factor is h to the power 0, so it is only g1. For n equal to 2 we have to calculate h bar to the power -1 g2 of x1 x2, and then this is h bar to the power 0, this is order 1, and then at order h bar, which is one loop contribution, you have these two diagrams, and then so on. If you calculate the 3-point function, that is h bar to the power, then you have to calculate h bar to the power -2 g3 x1 x2 x3, then that will be given by this. This is of course tree level, so 1, and then at one loop level you have these diagrams. So these are one loop contribution. So you see that G1, which is the 1-point function, that has leading contribution is h bar contribution, which is a quantum contribution, which means that at tree level or classically G1 is 0, and that must be the case because G1 is a 1-point function which is given by the curly phi. 1-point function means vacuum excitation value of this. We will have a detailed discussion now on this, and not having classical contribution means that we had chosen phi equal to 0. We had chosen the perturbative expansion around phi equal to 0, if you remember that potential. So let us discuss this now, what it means and how to deal with this 1-point function, the quantum contribution to this 1-point function in the next part. So let us recall. The discussion is question is how to deal with quantum generated 1-point function. That is the question we're going to focus on. So recall the classical vacuum picture. we had plotted that against constant value of phi, the potential that we are plotting is half m square phi square minus g over factorial 3 phi cube, and this is phi equal to 0. This phi is a constant value of field phi x. This constant value was due to Lorentz invariance. Right. What we did is that we said that what are the what will be the local minimum around which we are doing the perturbative expansion. So this local minimum should be a classical solution, but the classical solution for phi x will break Lorentz invariance of the theory around it. If phi x is a non-trivial profile, we should instead have a constant profile. So that was the argument, and then we plotted the potential for the constant profile. Kinetic term is 0, and we plotted the potential term, and we found the minimum, and that's where we shifted the field in such a way that phi is equal to 0 and the potential is also equal to 0 at that local minimum. And that is that local minimum around which the quantization has been performed corresponds to the interacting theory vacuum. So this is the local minimum around which quantization has been performed. And this corresponds to vacuum state of interacting theory in canonical quantization. The more precise relation is that more precise relation is that this phi is equal to 0 equal to phi is equal to the vacuum expectation value of phi hat of x. This is again to motivate such a relation, you should go back to the non-relativistic quantum mechanics. So recall non-relativistic quantum mechanics, say of harmonic oscillator. There you have a potential say half x square, right? So with this potential, you are calculating, you are doing the canonical quantization of the oscillator, and then you find the vacuum state, which is the 0 corresponding to 0 point energy. You find a vacuum state which is Gaussian like this. So this is psi 0 of x. This is the Schrodinger wave function. of the vacuum state. And if you call this so that is, so if you calculate the vacuum expectation value of the exact operator, right, then that corresponds to this position, this location, which is equal to 0. You could call it A, and you could consider a shifted harmonic oscillator. So a shifted harmonic oscillator will have the same picture here, half x square, but the potential is now shifted here. Okay, in this case you have a 0-point energy, and the Gaussian wave function for the for the vacuum is psi 0 of x will look like this. So it is for the usual harmonic oscillator, and this is for the shifted harmonic oscillator. In this case, this is say A. In this case, it is the potential is not half x square, rather half x minus a whole square. And there, if you calculate the vacuum expectation value of x, then you will get A, which is non-zero. Right. So I mean this half x minus a whole square is for the plot. This plot is for half x minus a whole square. So in the similar way, if you calculate the vacuum expectation value of the quantum field, then whatever the value of that is if it's a Lorentz invariant vacuum, the vacuum state is Lorentz invariant, then it will give you a constant, and for that constant you can calculate the potential, and it is this in the same interpretation you are going to arrive at. And if you calculate the potential, because if you calculate the minimum energy configuration for that configuration, the kinetic energy is 0 because the derivatives are 0, then you will basically draw this potential for the for this constant field configuration and the minimum energy, and you have chosen this to be the minimum energy configuration. Now, in field theory, we had done some calculations and saw that although at the classical level, the theory, this actually is 0, which means that the vacuum corresponds to constant phi equal to 0. But quantum mechanically, it is becoming non-zero. It is quantum mechanically generated. So that means in the same theory, if you start out with the same theory, but then quantize it, the vacuum is somehow shifting to a non-zero value. It is shifting to from the 0, right? So the quantum corrections are shifting the quantum corrections are shifting the minimum energy configuration in some sense, though we cannot see it clearly in this picture because this picture is valid only at the classical level. After the calculation, we saw that at tree level this is 0, but at quantum mechanical level this picture must change. This picture must change. And what exactly, how to study this picture in the quantum theory is the next question that we should explore. so that we can understand this picture better, because this is only a classical picture. So this is what we would do eventually, but before that, it's a so this part is an aside, just to give a non-relativistic analogy to what is happening here. Now quantum mechanically being this quantity being generated quantum mechanically, and so on, and this is becoming non-zero. So these can be considered as quantum corrections. And the question is that although the tree level, at the tree level, the classical although at tree level the classical picture remains the same, I mean classical picture is valid, we do not have a quantum corrected picture of this diagram, of this plot. And how should we deal with this? So we will be answering this question in two stages. First is that before so this is a more general question: what is the quantum version of this picture? We shall answer that question at a later stage. Before that, that's a more general question, but for this specific question, one-point function, we have a cure or some type of modification, a picture, a procedure that is more satisfactory than actually having having this G1 to be non-zero in your theory. You can set it to 0 through certain procedure, and that is what we should we will first focus on, and then later on, after that, we will go on to develop a quantum version of this picture, which of course will have this procedure as a subtopic or sub procedure, as a part of the procedure of this more complete picture. That picture is the picture of effective action, which will be discussed later. Now this is called, so all these diagrams you could write as this, where all these diagrams are appearing, some of these, and this is called a tadpole diagram. This is called a tadpole contribution. So the question is that, is it possible to get rid of tadpole? The answer is yes, and that is the procedure we will be describing in the next part.